Philosophiæ Naturalis Principia Mathematica, often referred to as simply the Principia, is a work in 3 books by Sir Isaac Newton, in Latin. First published 5 July 1687. After annotating and correcting his personal copy of the first edition, Newton also published 2 further editions, in 1713 and 1726. The Principia states Newton's laws of motion, forming the foundation of classical mechanics, also Newton's law of universal gravitation, and a derivation of Kepler's laws of planetary motion. The Principia is justly regarded as one of the most important works in the history of science. The French mathematical physicist Alexis Clairaut assessed it in 1747. The famous book of mathematical principles of natural philosophy marked the epoch of a great revolution in physics. The method followed by its illustrious author Sir Newton spread the light of mathematics on a science which up to then had remained in the darkness of conjectures and hypotheses. A more recent assessment has been that while acceptance of Newton's theories was not immediate, by the end of a century after publication in 1687, no one could deny that a science had emerged that, at least in certain respects, so far exceeded anything that had ever gone before that it stood alone as the ultimate exemplar of science generally. In formulating his physical theories, Newton developed and used mathematical methods now included in the field of calculus, but the language of calculus as we know it was largely absent from the Principia. Newton gave many of his proofs in a geometric form of infinitesimal calculus, based on limits of ratios of vanishing small geometric quantities. In a revised conclusion to the Principia, Newton used his expression that became famous, hypotheses non fingo. Contents expressed aim and topics covered in the preface of the Principia. Newton wrote, "Rational mechanics will be the science of motions resulting from any forces whatsoever, and of the forces required to produce any motions, accurately proposed and demonstrated, and therefore we offer this work as mathematical principles of philosophy. For all the difficulty of philosophy seems to consist in this, from the phenomena of motions to investigate the forces of nature, and then from these forces to demonstrate the other phenomena. The Principia deals primarily with massive bodies in motion, initially under a variety of conditions and hypothetical laws of force in both non-resisting and resisting media, thus offering criteria to decide, by observations, which laws of force are operating in phenomena that may be observed. It attempts to cover hypothetical or possible motions both of celestial bodies and of terrestrial projectiles. It explores difficult problems of motions perturbed by multiple attractive forces. Its third and final book deals with the interpretation of observations about the movements of planets and their satellites. It shows how astronomical observations prove the inverse square law of gravitation, offers estimates of relative masses for the known giant planets, and for the Earth and the Sun, defines the very slow motion of the Sun relative to the solar system barycenter, shows how the theory of gravity can account for irregularities in the motion of the Moon, identifies the oblateness of the figure of the Earth, accounts approximately for marine tides, including phenomena of spring and neap tides by the perturbing gravitational attractions of the Sun and Moon on the Earth's waters, explains the precession of the equinoxes as an effect of the gravitational attraction of the Moon on the Earth's equatorial bulge, and gives theoretical basis for numerous phenomena about comets and their elongated, near-parabolic orbits. The opening sections of the Principia contain, in revised and extended form, nearly all of the content of Newton's 1684 tract De Motu Corporum and Gyrum. The Principia begin with definitions and axioms or laws of motion, and continues in 3 books. Book 1, De Motu Corporum. Book 1, subtitled De Motu Corporum, concerns motion in the absence of any resisting medium. It opens with a mathematical exposition of the method of first and last ratios, a geometrical form of infinitesimal calculus. The second section establishes relationships between centripetal forces and the law of areas, now known as Kepler's second law, and relates circular velocity and radius of path curvature to radial force, and relationships between centripetal forces varying as the inverse square of the distance to the center and orbits of conic section form. Propositions 11 to 31 establish properties of motion in paths of eccentric conic section form, including ellipses, and their relation with inverse square central forces directed to a focus, and include Newton's theorem about ovals. Propositions 43 to 45 a demonstration that in an eccentric orbit under centripetal force where the apse may move, a steady non-moving orientation of the line of apses is an indicator of an inverse square law of force. Book 1 contains some proofs with little connection to real-world dynamics, but there are also sections with far-reaching application to the solar system and universe. Propositions 57 to 69 deal with the motion of bodies drawn to one another by centripetal forces. This section is of primary interest for its application to the solar system, and includes Proposition 66 along with its 22 corollaries. Here Newton took the first steps in the definition and study of the problem of the movements of three massive bodies subject to their mutually perturbing gravitational attractions, a problem which later gained name and fame as the three-body problem. Propositions 70 to 84 deal with the attractive forces of spherical bodies. The section contains Newton's proof that a massive spherically symmetrical body attracts other bodies outside itself as if all its mass were concentrated at its center. This fundamental result, called the shell theorem, enables the inverse square law of gravitation to be applied to the real solar system to a very close degree of approximation. Book 2 part of the contents originally planned for the first book was divided out into a second book, which largely concerns motion through resisting mediums. Just as Newton examined consequences of different conceivable laws of attraction in Book 1, here he examines different conceivable laws of resistance. Thus Section 1 discusses resistance in direct proportion to velocity, and Section 2 goes on to examine the implications of resistance in proportion to the square of velocity. Book 2 also discusses hydrostatics and the properties of compressible fluids. The effects of air resistance on pendulums are studied in Section 6, along with Newton's account of experiments that he carried out to try to find out some characteristics of air resistance in reality by observing the motions of pendulums under different conditions. Newton compares the resistance offered by a medium against motions of bodies of different shape, attempts to derive the speed of sound, and gives accounts of experimental tests of the result. Less of Book 2 has stood the test of time than of Books 1 and 3, and it has been said that Book 2 was largely written on purpose to refute a theory of Descartes which had some wide acceptance before Newton's work. According to this Cartesian theory of vortices, planetary motions were produced by the whirling of fluid vortices that filled into planetary space and carried the planets along with them. Newton wrote at the end of Book 2 his conclusion that the hypothesis of vortices was completely at odds with the astronomical phenomena, and served not so much to explain as to confuse them. Book 3, De Mundi Systemat. Book 3, subtitled De Mundi Systemat, is an exposition of many consequences of universal gravitation, especially its consequences for astronomy. It builds upon the propositions of the previous books, and applies them with further specificity than in Book 1 to the motions observed in the solar system. Here he developed several of the features and irregularities of the orbital motion of the Moon, especially the variation. Newton lists the astronomical observations on which he relies, and establishes in a stepwise manner that the inverse square law of mutual gravitation applies to solar system bodies, starting with the satellites of Jupiter and going on by stages to show that the law is of universal application. He also gives, starting at Lemma 4 and Proposition 40, the theory of the motions of comets. for which much data came from John Flamsteed and Edmund Halley, and accounts for the tides, attempting quantitative estimates of the contributions of the Sun and Moon to the tidal motions, and offers the first theory of the precession of the equinoxes. Book 3 also considers the harmonic oscillator in 3 dimensions, and motion in arbitrary force laws. In Book 3 Newton also made clear his heliocentric view of the solar system, modified in a somewhat modern way, since already in the mid-1680s he recognized the deviation of the Sun from the center of gravity of the solar system. For Newton, the common center of gravity of the Earth, the Sun and all the planets is to be esteemed the center of the world, and that this center either is at rest, or moves uniformly forward in a right line. Newton rejected the second alternative after adopting the position that the center of the system of the world is immovable, which is acknowledged by all, while some contend that the Earth, others, that the Sun is fixed in that center. Newton estimated the mass ratios Sun, Jupiter and Sun, Saturn, and pointed out that these put the center of the Sun usually a little way off the common center of gravity, but only a little. The distance at most would scarcely amount to one diameter of the Sun. Commentary on the Principia. The sequence of definitions used in setting up dynamics in the Principia is recognizable in many textbooks today. Newton first set out the definition of mass. 6. The quantity of matter is that which arises conjointly from its density and magnitude. A body twice as dense in double the space is quadruple in quantity. This quantity I designate by the name of body or of mass. This was then used to define the quantity of motion, and the principle of inertia, in which mass replaces the previous Cartesian notion of intrinsic force. This then set the stage for the introduction of forces through the change in momentum of a body. Curiously, for today's readers, the exposition looks dimensionally incorrect, since Newton does not introduce the dimension of time in rates of changes of quantities. He defined space and time, not as they are well known to all. Instead, he defined, through time and space, as absolute, and explained, only I must observe, that the vulgar conceive those quantities under no other notions but from the relation they bear to perceptible objects, and it will be convenient to distinguish them into absolute and relative, true and apparent, mathematical and common, instead of absolute places and motions. We use relative ones, and that without any inconvenience in common affairs, but in philosophical discussions, we ought to step back from our senses, and consider things themselves, distinct from what are only perceptible measures of them. To some modern readers it can appear that some dynamical quantities recognized today were used in the Principia but not named. The mathematical aspects of the first 2 books were so clearly consistent that they were easily accepted. For example, Locke asked Huygens whether he could trust the mathematical proofs, and was assured about their correctness. However, the concept of an attractive force acting at a distance received a cooler response. In his notes, Newton wrote that the inverse square law arose naturally due to the structure of matter. However, he retracted this sentence in the published version, where he stated that the motion of planets is consistent with an inverse square law, but refused to speculate on the origin of the law. Huygens and Leibniz noted that the law was incompatible with the notion of the ether. From a Cartesian point of view, therefore, this was a faulty theory. Newton's defense has been adopted since by many famous physicists. He pointed out that the mathematical form of the theory had to be correct since it explained the data, and he refused to speculate further on the basic nature of gravity. The sheer number of phenomena that could be organized by the theory was so impressive that younger philosophers soon adopted the methods and language of the Principia. Rules of reasoning in philosophy, perhaps to reduce the risk of public misunderstanding. Newton included at the beginning of Book 3 and 3rd editions a section entitled Rules of Reasoning in Philosophy. In the 4 rules, as they came finally to stand in the 1726 edition, Newton effectively offers a methodology for handling unknown phenomena in nature and reaching towards explanations for them. The four rules of the 1726 edition run as follows. Rule 1. We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Rule 2. Therefore to the same natural effects we must, as far as possible, assign the same causes. Rule 3. The qualities of bodies, which admit neither intensification nor omission of degrees, and which are found to belong to all bodies within the reach of our experiments, are to be esteemed the universal qualities of all bodies whatsoever. Rule 4. In experimental philosophy we are to look upon propositions inferred by general induction from phenomena as accurately or very nearly true, notwithstanding any contrary hypothesis that may be imagined, till such time as other phenomena occur, by which they may either be made more accurate, or liable to exceptions. This section of rules for philosophy is followed by a listing of phenomena, in which are listed a number of mainly astronomical observations that Newton used as the basis for inferences later on, as if adopting a consensus set of facts from the astronomers of his time. Both the rules and the phenomena evolved from one edition of the Principia to the next. Rule 4 made its appearance in the third edition. Rules 1 to 3 were present as rules in the second edition, and predecessors of them were also present in the first edition of 1687, but though they had a different heading, they were not given as rules, but rather in the first edition the predecessors of the three later rules, and of most of the later phenomena, were all lumped together under a single heading, hypotheses. From this textual evolution, it appears that Newton wanted by the later headings, rules and phenomena, to clarify for his readers his view of the roles to be played by these various statements. The first rule is explained as a philosopher's principle of economy. The second rule states that if one cause is assigned to a natural effect, then the same cause so far as possible must be assigned to natural effects of the same kind. For example, respiration in humans and in animals, fires in the home and in the sun, or the reflection of light whether it occurs terrestrially or from the planets. An extensive explanation is given of the third rule, concerning the qualities of bodies, and Newton discusses here the generalization of observational results, with a caution against making up fancies contrary to experiments, and use of the rules to illustrate the observation of gravity and space. Isaac Newton's statement of the four rules revolutionized the investigation of phenomena. With these rules, Newton could in principle begin to address all of the world's present unsolved mysteries. He was able to use his new analytical method to replace that of Aristotle, and he was able to use his method to tweak and update Galileo's experimental method. The recreation of Galileo's method has never been significantly changed, and in its substance, scientists use it today. General Scholium. The General Scholium is a concluding essay added to the second edition, 1713. It is not to be confused with the General Scholium at the end of Book 2, Section 6, which discusses his pendulum experiments and resistance due to air, water, and other fluids. Here Newton used what became his famous expression hypotheses non fingo, I contrive no hypotheses, in response to criticisms of the first edition of the Principia. Newton's gravitational attraction, an invisible force able to act over vast distances, had led to criticism that he had introduced occult agencies into science. Newton firmly rejected such criticisms and wrote that it was enough that the phenomena implied gravitational attraction, as they did, but the phenomena did not so far indicate the cause of this gravity, and it was both unnecessary and improper to frame hypotheses of things not implied by the phenomena. Such hypotheses have no place in experimental philosophy. In contrast to the proper way in which particular propositions are inferred from the phenomena and afterwards rendered general by induction, Newton also underlined his criticism of the vortex theory of planetary motions of Descartes, pointing to its incompatibility with the highly eccentric orbits of comets, which carry them through all parts of the heavens indifferently. Newton also gave theological argument From the system of the world, he inferred the existence of a Lord God, along lines similar to what is sometimes called the argument from intelligent or purposive design. It has been suggested that Newton gave an oblique argument for a Unitarian conception of God and an implicit attack on the doctrine of the Trinity, but the general scholium appears to say nothing specifically about these matters.